Okay, the extra practice problems for chapter 10. Number 1, convert 25 degrees Celsius into Kelvin. We just add 273.15 to it, and that's going to end up giving us 298.15, but this one goes to the tenths place, so our answer has to go to the tenths place, because when you're adding and subtracting, you go to the least precise, and that would be to the tenths place. So our answer has to be 298.2 Kelvin. There's no degree symbol, it's just Kelvin. Number 2, dry ice has a temperature of 195 Kelvin. What is the temperature in degrees Celsius? Well, here you would go 195 Kelvin minus 273.15. Negative 78.15, but this goes to the ones place, so our answer has to be negative 78 degrees Celsius. Remember, adding or subtracting, got to go to the least precise, which is the ones place, so that limits us. Number 3, a balloon contains 149.6 mils of gas at a pressure of 567 torr. If the temperature doesn't change, what is the volume of the gas at a pressure of 981 torr? Well, here we use P1V1 equals P2V2. And we are given that the volume of the balloon initially is 149.6 mils, and that this has a pressure of 567 torr. The temperature doesn't change. That was why we were able to take away these. We didn't have to worry about those in this particular problem. What is the volume? So we're looking for V2, and the new pressure is 981 torr times V2. So we're going to divide both sides by this. That will leave V2 by itself over here. We have 3 significant figures in 2 of these, so our answer has to be in 3 significant figures. The torr is going to be left, so we're going to be left with 86.5 mils. And that would be our new volume. Number 4, a flexible container starts with a volume of 16.7 liters at a temperature of 25 degrees Celsius. If the pressure doesn't change, what is the volume if the temperature rises to 150 degrees? All right, so I'm just going to leave over here P1 V1 over T1 equals P2 V2 over T2. All right, and in this particular case, we're told the pressure doesn't change, so we're going to cancel that out. So we're going to be left with V1 over T1 equals V2 over T2 because the pressure doesn't change. Okay, and so then we have a volume initially of 16.7 liters, and the temperature is 25.0 degrees Celsius. We know we are not allowed to use anything but Kelvin, so we're going to go 273.15. So that's going to give me 298.2. 298.2 Kelvin equals the new, let's see, if the pressure doesn't change, what is the new volume? So we were looking for V2, and the new temperature is 150 degrees Celsius, 273.15. So it's going to give us 312, carry the 1, 423.15. Okay, which is going to end up being 423.2 because you can only go to this place. So we're going to take this out and make it a 2. So I put that there. All right. Make sure you do your conversions to Kelvin. So now we're going to multiply this over here so that we can have V2 by itself. There we go. There. Now we have 4 significant figures, 3 and 4. So our answer has to be in 3 significant figures. So what I get out of, yep, that one's there. Okay, so this one is 23.7. Kelvin will leave and I'll be left with liters, which is good because we're looking for a volume. So that took care of that. Number 5. A gas-filled balloon has a volume of 15 liters at ground level where the temperature is 25 degrees and the pressure is 1.01 atmospheres. It rises to an altitude where the temperature is negative 12.1 degrees Celsius and the pressure is 0.10 atmospheres. What is the volume of the balloon? So in this case, we're going to use the whole thing. And so the gas balloon, the first volume is 15.6 liters. Ground level, the temperature is 25 degrees Celsius plus 273.15. That's going to give me 298.2. So I'm going to put in here 298.2 Kelvin. And the pressure is 1.01 atmospheres. Okay, so there's P1, V1, and there's T1. And now we go to the next. It rises to an altitude where the temperature is negative 12.1 degrees Celsius plus 273.15 gives me 261.05. Rises to an altitude. Okay, so the new temperature is 261.1 because we can't use that because that goes to the tenths place. So this has got to go to 0.1, okay, Kelvin. And the atmosphere, the new atmosphere is 0.10. Notice two significant figures, atmospheres. And we are looking for the new volume. There it is. Okay, so if we go ahead and we do that number over there, three significant figures, I get 0.0528 atmospheres, liters per Kelvin. Now, I'm going to get V2 by itself, so I'm going to multiply this by 261.1 Kelvin and divide it by 0.10 atmospheres. Okay, if I do that, then I can get V2 by itself. I multiply that and divide it by that. So when I do this, I have to have an answer in two significant figures. I'm going to put it up here so you can see it. 137.95. And notice atmospheres will leave, Kelvin will leave, whoops, and we'll be left with liters. So this is liters. But I can't do this because I only have two significant figures. So this and two significant figures would be 140. So your answer would be 140 liters. Number 6. How many moles of water vapor are present in a 615 ml container at 21.5 degrees Celsius at 745 torr? So here we're asked for moles, so we're going to use PV equals nRT, the ideal gas law. And we're looking for moles, so I'm going to go ahead and solve this here because it'll just make it a little cleaner. So I just divided both sides by RT. Okay, then let's see what we're given. We're given the original pressure at 745 torr. Excuse me, not the original pressure, the pressure. The volume is 615 mils. But we have to have this in liters, don't we? Because R, oh boy, and the R is going to be in atmospheres liters. We're going to have to make some changes because remember R is 0.0821 atmospheres liters per moles Kelvin. And because of that, we've got to take the torr, 745 torr, and we've got to turn that into atmospheres. And in one atmosphere, there's 760 torr. And so that's going to end up giving us 0.980 atmospheres. So now I can put that in for my pressure, 0.980 atmospheres. And then I need the volume. Well, the volume is given to me as 615 mils, but I have liters here, so I'm going to make it 0.615 liters. Okay, so I converted the mils to liters. There's T. Now let's look for the temperature. The temperature we're given at 21.5 degrees Celsius plus 273.15 is going to give us 294.65, but this goes to the tens place, so this is going to be 294.7 Kelvin. 294.7 Kelvin. Okay, and then that is going to give us, when you get rid of the Kelvin, the liters, the atmospheres, you'll have moles left. There's 4 figures here, 3, 3, 3. So we should have 3 significant figures, which is going to be 0.0249 moles of water vapor. Here you go. Now, the trick to this one was because of R is in liters, atmospheres per mole Kelvin, you had to convert your torrs to atmospheres and you had to convert your milliliters to liters. If you didn't do that, everything would have been off severely. Number 7, what is the volume of 100 grams of ammonia at 84.5 degrees Celsius and a pressure of 869 torr? Okay, so here we're still going to use PV equals nRT, but what we're asked for here is the volume. So I'm going to solve for V. So I'm just going to divide both sides by P. So I'm going to go like this. Okay, first thing we're going to need is the moles. That's what N represents, and we're told we have 100 grams of ammonia . For every 1 mole of this, it is 17.04 grams, and so that's going to give us 5.869, 4 significant figures, moles of ammonia. So we got our first thing, so I'm going to go ahead and stick that in. 5.869 moles. Okay, R we have memorized, 0.0821 liters, atmospheres, mole Kelvin. Temperature. The temperature we're given as 84, get rid of this, 84.5 degrees Celsius. We need to get it to Kelvin, 273.15. That's going to give us 357. We've got to go to the tenths place, so we're going to roll this up to 7. So here we have 357.7 Kelvin. Okay. And then we're going to divide that by the pressure. Well, here we're given the pressure is 869 torr, but we know we have to have atmospheres, so we're going to go like this, and we're going to go torr, atmospheres, 760, and so that's going to end up giving us three significant figures because that one it doesn't count in. And so this is going to give us 1.14 atmospheres. So I'm going to put that in. 1.14 atmospheres. Excuse me. Now the atmospheres will cancel, moles will cancel, Kelvin will cancel. We'll be left with liters, which is what we're looking for. We have three significant figures, 4 in a couple places, but 3 in 2 other places. So we're going to want our answer to be in 3 significant figures. And so what I get is 151 liters, 3 significant figures. Number 8, how many liters of hydrogen are made at 25 degrees Celsius, 1.12 atmospheres, when 25 grams of magnesium react with an excess of HCl according to the following equation? And there we have the equation. All right, so we have 25 grams of magnesium, and it reacts with excess of this. Okay. And we want to know how many liters of hydrogen are made. Okay, so we're going to start here, we're going to drive to here. We know that because there's the numbers, there's the question mark. So we got to go through the mole tunnel. So we're going to go 25.0 grams of magnesium times line, the grams of magnesium to the moles of magnesium. And so 1 mole of magnesium is 24.31 grams, which is going to give you in 3 significant figures 1.3 moles of magnesium. Now, if you go through the moles, the stoichiometry, notice it's a 1-to-1 relationship. So I know I have that many moles of hydrogen also. So I'm going to come over here and put 1.03 moles of H2. And in case you're wondering, that was 1 mole of magnesium here, 1 mole of H2 here, and that's how I got that. Through the stoichiometry, because it's a 1-to-1 relationship. And that's important because if it wasn't a 1-to-1 relationship, this number of moles would be different. So you had to figure that out. And so then we are told, we want to know how many liters of hydrogen are made. Well, we have the number of moles, but we don't have the number of liters. To figure that out, we're going to use PV equals nRT. And we're trying to find out the number of liters. So we're going to divide by P, both sides. That would give us our volume. We have the number of moles is 1.03 moles. We have 0.0821 liters atmospheres per mole Kelvin. We have the temperature given to us as 25 degrees, so we know that plus 273.15 is going to give us 298.2 Kelvin. I only know that because we've done it like 8,000 times now, right? Divided by, and the pressure we're given as 1.12 atmospheres. Thank you, Jesus. It was in atmospheres already. So the atmospheres will cancel, the moles will cancel, Kelvin will cancel, we'll be left with liters. 3 significant figures, 3, 4, 3. So our answer is going to be in 3 significant figures. And so our answer is going to end up being 22.5 liters. 22.5 liters. Number 9, a chemist wants to make 6 liters of ammonia according to the following reaction. How many liters of hydrogen will she need at STP? These are all gases. We are asked for how many liters of this, and we are told that we start with 6 liters of this. So remember, with them all being gases, we can go through this like it's stoichiometry. So we can go 6 liters of NH3 times line, NH3 on the bottom, liters of H2 on the top. This gets a 2, that gets a 3. And so that's going to give us 9 liters of hydrogen gas. That one was easy because we were able to actually use the stoichiometry, but with the volume. Okay, let's see. Number 10. A balloon is filled with 715 torr of hydrogen gas and 345 torr of nitrogen gas. What is the mole fraction of each gas? Okay, so we have 715 torr of hydrogen gas. That's the partial pressure of hydrogen. And we have the partial pressure of nitrogen gas at 345 torr. And so we know that if we add these two up, which gives us 1,060 torr, that's our total. And we know that the mole fraction of H2 equals the partial pressure divided by the total pressure. So it's the partial pressure divided by the total pressure. Remember, this has 3 significant figures also. So our answer should be in 3 significant figures. 0.675. And for nitrogen, we do the same thing. 3 significant figures, that gives us 0.325. And that's what we were asked for, was the mole fraction of each. So you just take its partial pressure divided by the total partial pressure, and that gives you the mole fraction. A container holds 0.54 moles of argon. It tells us the moles of each of these. If the total pressure of the gas is 5.1 atmospheres, what is the partial pressure of each gas? Well, we know that the mole fraction, let's say of A, equals the partial pressure divided by the total pressure. That's what we just did a minute ago. And so, let's see, we are given argon, so the mole fraction for argon is 0.54 moles. We're given that the mole fraction for hydrogen gas is 0.92 moles. For nitrogen gas, it's 0.45 moles. Okay, so first we need to find the total pressure. And so we do that by converting, we want to find the mole fraction. And so for argon, it would be the mole fraction times the pressure total. And we're told that the pressure total equals 5.1 atmospheres. So we're going to take this to find argon. We're going to take this and go the mole fraction times the total pressure. And we're going to have an answer in two significant figures. Then we're going to do that for hydrogen, which is the mole fraction times the total pressure. And then this last one here, we're going to find the mole fraction and the total multiplied by it. We have to have all these answers in two significant figures. Guys, would you shut that door, please? And I'll tell you when. We have to have the mole fraction in two significant figures. So this is going to be 1.4 atmospheres. This is going to be 2.4 atmospheres. And this is going to be 1.2 atmospheres. Okay, now there's your partial pressures. Last problem. Yay! A chemist makes oxygen gas by decomposition of a hydrogen peroxide, and it shows us the equation. He collects the oxygen over water in which the reaction is taking place. If he collects 1.45 liters of oxygen, and it tells you the atmospheres and the temperature, how many moles of oxygen gas did he make? And we're allowed to use the table on page 311. Okay, so we have the equation. Okay, there's our equation. And how many moles of oxygen? That's what we're looking for. Collects the oxygen over the water in which the reaction is taking place. And we're given the volume, the atmosphere. So we are going to use PV equals nRT. All right, we know we're going to be solving for moles. So it's going to be PV over RT. Now the first problem we have is the pressure. And we know that the total pressure equals the pressure of the water vapor and the partial pressure of the water vapor and partial pressure of the oxygen. If you look in your textbook at the table on page 311, you'll notice that the partial pressure of the water at this temperature is 31.8 torr. But you have to have that in atmospheres because this is in atmospheres. And so you're going to go times line, torr, atmospheres, one of these, 760 of these, and that's going to give us 0.0418 atmospheres. Okay, that is the total pressure in atmosphere. Excuse me, that is the partial pressure of the water. The total pressure was given to us, so the total pressure is 0.921 atmospheres, And that total pressure equals the partial pressure of water, which we just converted to atmospheres, plus the partial pressure of the oxygen. So if you solve for this, the partial pressure of the oxygen, I'll just put it over here, the partial pressure of the oxygen equals 0.879 atmospheres. Now, we've got the partial pressure of the oxygen, so we can come back over here and start plugging in. So N equals, P for the oxygen is 0.879 atmospheres. See, if you just put in what was given, that was the total pressure, including the water vapor pressure, and that's why you couldn't just stick that in. You had to find the partial pressure of the oxygen to stick that in. And then we're given the volume as 1.45 liters. And then, let's see, we're dividing by R, which is 0.082. Yeah, I got that right. 0.0821 liters, atmospheres, moles, Kelvin. And then the temperature we had as given to us as 30 degrees, and we add to that 273.15. I'm going to show you. 30 degrees plus 273.15. So that's going to give us 303.2 Kelvin. So I'm going to stick that in here. 303.2 Kelvin. And so we have three significant figures: Kelvin, atmospheres, liters. We're left with moles. And so when you do this, you get 0.0512 moles. And so that is how you find the moles of oxygen gas that he made. Now, the place that people might mess up is by just putting in the total pressure here instead of finding the partial pressure for the oxygen. And he kind of cues you when he tells you it's collected over water and you can use the table. So that was a cue that you needed to use that. Anyway, I know it's a lot of work, but show all your work, study this, take your test, and read the first half of the next chapter. Have a Jesus-filled week.